So here we have a question which says that Elena has 12 distinct blocks, two each of red, blue, yellow, green, orange, and purple. Call an arrangement of blocks even if there is an even number of blocks between each pair of blocks of the same color. For example, the given arrangement is even. Then how many such arrangements are possible? It is given to us RBBYGG, YROPPO. So, quite an amazing question, and let us now have a look at the correct solution. So basically, the number of positions, since there are 12 letters or 12 blocks, let us just name the positions as 1, 2, 3, 4, all the way up till 12. So something like this: first block, second block, third block, fourth, all the way up till 11th and 12th block. Now, let there be an even number of blocks, let's say 2m, between the two blue boxes. If the position of the first blue box is P, and then the position of the next blue box would clearly be Q equals to P plus 2m plus 1, right? So it is very similar. Let's say some box is on fifth position, and let's say there are four blocks between this, and then we have the next, the next blue box. So obviously its position would be 5 plus 4 plus 1, right? Because 6, 7, 8, 9, but then 10. So 5 plus 4 plus 1 would obviously have to be done for the next position. So that's why position plus 2m plus 1 we have done here. It is a very simple observation, so nothing difficult. Clearly, if P is even, then Q is odd, because look, this entire number is odd, so odd plus even is odd only. Whereas if P is odd, then odd plus odd would give us basically an even number, so Q would be even. Now consider the two boxes at positions. So what we have proven here is that if there are an even number of blocks between the boxes, then if one of the positions is even, the other would be odd. And if the other is even, the first would be odd. So out of the two boxes, one would be at an odd numbered position, the other box would be at an even numbered position, is what we have proven till now. Now we are also proving its converse. Let us consider that the two blue boxes are at positions R and S such that one of R comma S is even while the other is odd. Clearly, the number of boxes between the blue boxes would be magnitude of R minus S minus 1. It is as simple as saying that, let's say, one of the boxes is at a position 6, the other is, let's say, at a position, let's say, 6, 7, 8, 9, 10, let's say. So basically, what is the number of boxes between them? So it's obviously 10 minus 6, 4 minus 1, right? So that is because here in this case there are three boxes. So one would be subtracted in order to get the number of boxes between them. It's a very simple observation. So, but if one of them is even while the other is odd, then even minus odd or odd minus even would anyway result in an odd number. So it is obviously odd. But if we subtract one from it, it would obviously come out to be an even, just like we had wanted. In the question itself, it wants that the number of boxes between them should be an even number of boxes. So we have proven that, and for an arrangement to be even, the necessary and sufficient condition means it will be even if and only if the boxes of same colored are placed such that one of them is at an odd numbered position while the other is at an even numbered position. Clearly, the even numbered positions are 2, 4, 6, 8 all the way up till 12, and odd numbered positions are 1, 3, 5 all the way up till 11. So we need to first pair up the even positions with the odd positions, which will determine the even odd position pairs containing the same colored boxes. So in this given example, we can see that the red box is at the, or rather the blue box is present at the position 2, 3. So this is one of the pairs of positions. This is one of the position pairs. Then similarly for green, we can see the position pairs are, or rather for yellow, we can see they are 4, 7, because obviously this is the fourth position, this is the seventh position. So this is another position pair. Then for basically 6, 5, we can see it is the G and G, right? So GG, both the greens are present at this position pair 6, 5. Then similarly, 8, 1 is present for the red box. This is at position 1, this is at position 8. Similarly, 10, 11, and 12, 9. So they also cover PP and OO. So what we are saying is that we first need to find, basically pair up the even positions with odd positions, because here also we can see that one of them is even, the other is odd, even odd, even odd, even odd, even odd, even odd. Obviously that has to happen because we have already proven that one of them will be at an odd numbered position while the other would be at an even numbered position. So we have to make these kind of pairs, 6 pairs, each pair containing one even while the other odd. So obviously the number of ways of, so these are the odd positions, these are the even positions. So the number of ways of pairing them up is simply 6 factorial, because pairing is simply mapping. Like we can map 1 with 6, let's say 3 with 12, let's say 5 with 2, let's say then 7 with 8. Any random pairing we can do that might look something like this. So basically arranging the 1 3 5 7 all the way up till 11 in these 6 position would be simply 6 factorial. So the pairing can be done in 6 factorial ways. Now call these position pairs as p1 p2 p3 till p6. So for example, let's say we have made any particular position pairs, so call them p1, then p2, p3, p4, p5 all the way up till p6. Fine. Now, once we have made them, we obviously need to assign the colors which will be present in those position pairs. So, for example, in this 2, 3, we have the blue color assigned to this position pair, right? So, in this example given to us, P1 is assigned the color blue. The position pair 2, for example, is assigned the color G, right? So, similarly, position 3, P3 is assigned basically 5, 6, which means it is assigned the color. So I think for P2, which is 4, 7, it is actually assigned the color yellow or Y, right? Then similarly, P3 is assigned the color G, right? This position pair of 5, 6 contains G or the green color. So obviously, once we have the position pairs, we need to assign the 6 colors to the position pairs, which can obviously be done in 6 factorial ways, because there are 6 colors and 6 position pairs. So in 6 factorial ways, we can arrange or assign them. Then in each position pair, the boxes of the color assigned to it can obviously be arranged in 2 ways, 2 factorial ways. So let's say for the blue color, we have blue box 1, blue box 2. Obviously, all boxes are given distinct. And let's say the position pair selected for this is, let's say, 8, 11. Then obviously, they in the 8th and 11th position, these two boxes can be arranged in 2 factorial ways. B1 can go here, B2 can go here, or B2 can go here, B1 can go here, right? So hence the total number of arrangements is given by the multiplication principle, 6 factorial into 6 factorial into 2 factorial power 6, because we are arranging the two boxes of each of the 6 colors. So 2 factorial into 2 factorial into 2 factorial 6 times. So that gives us the final answer. So I hope you all were able to understand. Thank you for watching.